Today I'm going to teach you about electric motors, and electric motors are really exciting because right now they're found everywhere, and now with everyone's vehicle becoming electric, it's really exciting. There's lots of new technology coming out, and so today I want to give you an understanding of how these motors work and how the conversion from electrical energy turns into mechanical rotational energy. And so first of all, why should you care about how electric motors work? Well, according to the Department of Energy, which is a US agency, 68% of all the energy produced is used by electric motors. In your house, you could probably think of a few examples. So you have like fans in your house for cooling, you have your electric toothbrush, you have your washing machine. All these have electric motors and you use them almost daily. They have, and then in industry, you have motors that pump water. Here you can see a picture of, these are motors in a pump house. And so in California, there's many pump houses. This is how we get our water. And this motor turns a pump that's located down in the ground and pulls up water. And this is how you get water to your spigot in your house. And so if we didn't have these motors, then it'd be very difficult to get anything accomplished. The other reason you should care is by 2035, all new cars and passenger trucks sold in California will be zero emission vehicles. And so, so that basically means it's going to have electric motor. And so by listening to my presentation, well, hopefully you'll understand how it works, and maybe you'll see some benefits or some drawbacks to having an electric motor. There's three types of electric motors. The first type of electric motor is the permanent magnet motor. And that's this motor that I show on the left here, and it's been painted green. This motor has permanent magnets in it. These permanent magnets, I'll get into this a little bit later, but they're right here. And then the second type of motor is the induction motor. This is what Nikola Tesla conceived. And in this motor, there's no permanent magnets at all. Essentially, you have the rotor, which is the part that spins, and it's been pulled out of the motor right now, is made of just aluminum, basically like a cast aluminum, and then the cast aluminum is cast into the steel, which has slots in it. And then you have reluctance motors. The reluctance motor, you can see the rotor is made of steel, and then it basically has these air pockets that are these really detailed air pockets that are in the actual rotor. And so the most common motor would be the permanent magnet motor and the induction motor. The reluctance motors are a lot less common. So what is an electric motor? An electric motor converts electrical power to mechanical power. And I denote electrical power, this PE, and the mechanical power is PM. And so you can think of a drill. Here you have your standard hand drill, and it has batteries which store the electrical energy. And when you press the trigger, the electrical energy is converted to a mechanical power, and that causes the chuck and the drill bit to spin. It's also important to note that all motors can also act as generators. And so instead of converting electrical power to mechanical power, a generator converts mechanical power back into electrical power. And that's how you get your power in your home. And there's an example of this is your hybrid vehicle. Imagine like the Toyota Prius. The Toyota Prius, imagine you're getting on the freeway. You press on the accelerator, the motor starts to accelerate the vehicle, and you start draining your battery because you're converting that electrical power into mechanical power. Well, now, you're on the freeway, you want to get off the freeway, so you have to hit the brake. When you hit the brake on a hybrid vehicle, the motor, the electric motor, will turn into a generator, and it'll basically suck power out of your motion and put that back into the battery. And so the reason they do this is because you get good all-around efficiency. You just restored that energy that you put into motion back into your battery. And so so that's something I just wanted to point out. So now I'm going to go into power conversion and how the electrical power is converted to mechanical power. And so power is torque times speed. And so what is torque? Torque is called a force at a distance. If you look at this picture of the dragster wheel that I have, you have your dragster wheel, and it has an axle, and it also has a place where the tire contacts the ground. And so the distance between the axle and the ground would be your distance, and then your force is the force that's exerted between the tire and ground. And so if you multiply the radius times the force, you get torque. And your speed, so the speed is also called an angular velocity. That's just a fancy term. And so the speed times the torque equals the mechanical power. So now I'm going to discuss the electrical power. Electrical power is a bit more complicated, but hopefully I'll try to make it simple so that you understand. So electrical power is voltage times current. And so to understand what voltage and current are, there's a really good water flow analogy. And so basically, if you look at this picture of this guy drinking this green shake, pressure would be the suction that he exerts with his mouth. And when you suck on a straw, that creates flow through the straw. And so the amount of flow that you get is dependent upon how big that straw is. If you have a small straw, it's really hard to get any flow of shake. It's really hard to drink the shake. But if you have a larger straw, it becomes a lot easier. You get more flow. And so you can think of this pressure as the voltage and the flow as the current. And instead of, in electrical circuits, you have flow of electrons. And so that's what current is. And so this power conversion, basically the mechanical power has to equal the electrical power. The power isn't lost mysteriously, nor is it created mysteriously. There's no such thing as free energy. And so you have to realize this what you put in electrically is what you get out mechanically. And so now I want to discuss the main components of electric motor. And what we're going to do is we're going to go into what the voltage and current is in a little bit more detail, give you a bit more understanding. So there's two main components to the motor. There's the stator, which is the stationary part. And the stator is essentially this green piece, which is called the stator yoke. And the stator consists of coils, which are conductive wires wrapped around. And so the stator is the stationary part of the motor. And it basically, this green part, the stator yoke is what holds the coils in place so that they don't move when the machine's operating, or they don't vibrate out of place. And you also have the rotor, and the rotor is the part that rotates. This would be the part that spins the tires on the car. And in this case, the rotor consists of permanent magnets, which are these small rectangular pieces. And it consists of a rotor core. The rotor core essentially holds the magnets in specific positions so that they don't move. And so this is, there's 4 components to the motor, to the permanent magnet motor, and these are the components. So now I want to get into how the magnets work. So when you make a permanent magnet, the magnet does not start off as magnetized. Essentially, when they make the magnet, they take a bunch of really finely ground up particles, and they put it into a mold, and they compress the mold, and that creates your magnet shape. And to turn this magnet shape into a magnetized magnet, you have to exert a really large magnetic field on the magnet. And so you exert this really large external magnetic field, and then you remove the field, and the permanent magnet will hold the magnetization. And so this magnetization, which I show to the right, it's essentially, it's oriented so that you have a north and south pole, and the magnetization is the result of electron spins in the atom aligning together. And so these magnets create these external fields that radiate from the actual physical material. And these fields are called the magnetic flux density. And so here you can see I've drawn the fields. They start at the north pole of the magnet, and they circle around and go to the south pole of the magnet. And these fields are given the units of Webers per square meter. And Weber is a unit of magnetic flux, and then meter squared is a unit of area. And so these fields are like essentially a density. And so if you think about it, the fields really close to a magnet are going to be really strong because they're very dense. And then the fields further away from the magnet are going to be a lot weaker. And so if you think about it, if you take a magnet and you move it towards your fridge, all of a sudden it gets really, really strong, and at some point you can't even stop it from sticking on the fridge. Well, that's because those fields get really dense as the magnet's close to the fridge. And so if you move the magnet, if you rotate it, the fields orient themselves the same way with respect to the north and south pole. And so this unit of Webers per square meter is also called the Tesla, after Nikola Tesla. So now I'm going to dig into like how the motor works a little bit more. I'm going to give you, I've kind of drawn out this simplified motor. So this motor, essentially you have a magnet, and you have 2 coils. You have coil A, which is this lighter yellow, and coil B, which is almost this orange color. And these are the most basic components that you can use to create an electric or permanent magnet motor. And with this motor, you essentially would apply a current to coil A and a current to coil B. And when this magnet spins, you induce voltages in the coil. And we'll go into what those voltages are in the next slide. So the first concept of understanding the electrical parameters of the motor, Faraday's law says that any change in the magnetic environment or magnetic flux of a coil or wire will cause a voltage to be induced in the coil. And this is Faraday's law right here. Faraday's law says there's a voltage induced if there's a change in flux with respect to the position of the magnet. And this is also multiplied by the speed of the motor. And so I'm going to get into a little bit more detail about what this change in magnetic flux is over divided by the change in position. So don't worry if you don't understand it right now. We'll come back to this. So here's how kind of like a motor works. Basically, I have 3 different diagrams of the motor, and each diagram of the motor, the magnet's in a different position. We start off with the magnet oriented in 0 degrees, where the magnet faces coil A. And then the second one, we rotate the magnet, so the magnet's now positioned between coil A and coil B. And then the third image, the magnet's oriented at coil B. And so you can see if you like take this coil and you almost like look at it directly, when the magnet's oriented towards coil A, you can see that there's some fields going through it, and these fields are going perpendicular through the coil. If you look at coil B though, the fields are going parallel to it. And so you can get the idea that for coil A, you have all these fields going through it, and coil B, you have none. They're just going parallel to the coil. And then when we rotate the magnet now you have a few more fields that are going perpendicular to coil B. So your fields are starting to, you're starting to get some of the fields through it. And if you look at coil A, you essentially lost some of the fields, so the field density has changed. And now in the 90-degree case, the magnet's oriented at coil B, and you see you have all these fields going through it and none going through A. So you can get the idea that if you rotate the magnet, the magnetic flux or the magnetic field density in the coil is changing with position. Oh, there we go. And so there's another law involved in motors, and that's Gauss's law. And Gauss's law says that the amount of flux going through the motor is the magnetic flux density, which I said was Webers per meter squared, times the coil area. And so if you take the area of the coil and multiply it by all the fields that you see going through it, that's the total amount of flux going through it. And so here I have a video that I'm going to share with you guys that will kind of demonstrate, and so you can see the fields changing in the motor. Let me share it. So here on this motor, the magnets are actually located on the outside of the motor, and so you have these magnets, and you can see the fields that are darker color are more dense. So if it like this pink here and the orange are more dense versus the fields that are blue are less dense. And so you can see the fields in the motor are changing with the position of the magnet. And so that induces a voltage in the coil. So now returning to Faraday's law. So again, Faraday's law said any change in the magnetic environment or magnetic flux of a coil of wire will cause a voltage to be induced in the coil. And so this change in magnetic flux divided by the change in position of the motor is what's called the torque constant. And the torque constant is how strong the motor is. And so if you think about, like, if you have a bigger motor and a smaller motor, the bigger motor is going to have bigger coils, it's going to have more area, and so you're going to have a bigger area that the magnetic flux can pass through. And so the torque constant will be higher for a bigger motor because you get more change in flux as the rotor rotates. And so kind of putting it all together, we started off with the mechanical power equaling the electrical power. And then we broke it down, said that the mechanical power equals the torque times the speed. And then on the electrical power, we said, the voltage times the current in each coil was the electrical power. And if you apply sinusoidal excitations, so periodic excitations, then essentially what you get is you get that the mechanical power equals the torque constant times the current that you apply to the motor times the speed of the motor. And these, just to note, these current excitations are applied by a power inverter, or sorry, a power converter, or a drive unit. And usually this is what they call power electronics. And so this is like, I believe, one of the Tesla's power electronic packages. And so kind of revisiting the torque constant. So again, like I said, the torque constant is a measure of how strong the motor is. And so what makes one motor stronger than another? Well, it turns out the torque is proportional to the motor's radius squared times the length. And so what's this mean? It means that to get more torque out of a motor, you get a lot more torque if you make the radius bigger. And so ideally, your motor is going to look more like a pancake than a hot dog. So here, this top example, you can see the radius is really large and the length is really skinny. And so this motor has a lot of torque. And then you have this other motor where the radius is really small, but the length is really long. And so motors will tend to look like this upper one, like the pancake, because that's what gives it the most torque. The other thing that gives you more torque is your magnet strength. You've probably heard of rare earth magnets. Rare earth magnets give you the most energy, and that's what they call the energy product. So the higher the energy product, the more torque dense the motor. So what electric motors do cars have? There's pretty much two different types that they've been using in electric vehicles. There's the induction motor, which has been used in the Tesla Model S, I believe the Tesla Model X, and the Audi e-tron. And then there's other motor called the permanent magnet synchronous reluctance motor, which has been used in the Tesla Model 3, the Toyota Prius, the Nissan Leaf, Chevy Volt, you name it, it probably has it. And so what is this synchronous reluctance motor? Well, remember I was talking about the reluctance motor having a rotor that contained steel with air pockets? Well, what they do is they fill the air pockets with magnets. And so if you look on the picture on the right, you see these magnets, and they've been embedded into the steel on the motor. It looks a little bit different than the reluctance motor, but just think, in the reluctance motor, they would have just removed the magnets, but now they put them in there. And so this is pretty much what most vehicles use. So what's the rationale for the induction motor? Why do they choose one versus the other? Well, there's actually a pretty good reason. So the inductables, because there's no reliance on rare earth materials, so no reliance on magnets. And these magnets and rare earth materials are subject to price manipulation. So here's a plot on the right. Basically, China is the main producer of all rare earth metals, and so they control the price. And so back in 2011, there was a huge price spike where China caused the prices of the rare earth materials to skyrocket. And so by choosing an induction motor, then you don't have to deal with the price manipulation. But what's the rationale for the permanent magnet synchronous reluctance motor? Well, you get a little bit better efficiency, and the control strategy is a lot easier. So it's easier to control the motor, and have it make it do what you want.